Welcome back to additive manufacturing one more time. Today we're going to continue talking about CAD and CAE for additive manufacturing. And one of those opportunistic design methods that we really want to emphasize is topology optimization, right? So if we go back a couple lectures, remember we talked about restrictive versus opportunistic design for additive manufacturing, where opportunistic is really taking advantage of all the capabilities that additive manufacturing has to offer. Particularly this ability to place material almost anywhere we want it. So topology optimization is really one of those techniques, right? So let's take what is a reasonably simple structural problem like the one here in the upper left, where we're looking at just developing a sling here, right? So you're basically going to support some load that's going to be hanging down from the center. You've got braces, you've got a platform, you've got a crosshead over the top. And one of the things we want to do with that is topology optimize it, right? And so if we topology optimize it, what that does is it optimizes the placement of material to, for example, support a load with boundary conditions that help support that load, right? So maybe we've got boundary conditions, fixed boundary conditions along the bottom that tell us that we can support this load down here. With no displacement. So we've got rigid supports down there, and then we've got this load that's being applied across the top. So how do we get it down to those rigid supports? And a topology optimization algorithm will allow us to place material anywhere we want it to most efficiently support that load, right? With the least amount of material possible, but still getting the structure as stiff as possible, right? So as stiff as possible with the least amount of material. Now we can also go in and we can look here in the upper right, you can see some shape optimization problems where we then, after we topology optimize, we can then go and look at this little line here in teal, which adjusts the shape or contour of some of the things that we've generated with topology optimization. Now that's just changing the shape of it though. It's not adding additional holes or additional elements in certain locations. And then down here at the bottom here, if we look at this, we could also do size optimization, which is just taking one of these elements here. You can see the D, you can see the T, and it's just changing its dimensions as we go along, right? So topology optimization envelops all of those things. It's not just dimensions, it's not just shape, it's actually connectivity as well, right? How many elements do we have? Where do we have holes? And where do we place them? How are they sized? So we can do some really cool things with that, and people have done some really cool things with that. So here's a practical problem. This was a challenge problem from GE to design a bracket to hold on part of repair accessibility door on an engine, an aircraft engine. And you can see how the original part here at the top was built to be machined. And then you can see the part at the bottom that was built to be additively manufactured using topology optimization. I believe it has about the same stiffness, but half the weight of the original machined component, right? And then here on the bottom here, we can see this is an example of a partition that separates the crew seating from the passengers. And one of the things you'll notice here is how cool this underlying structure looks like over here. And that structure there has been topology optimized using some generative or biomimetic design to make it as lightweight as possible. And it's almost 50% lighter than the previous partition that was used, which then of course translates into fuel savings and things like that for the aircraft. And then here you can see here on the right-hand side, you can see topology optimized framework for an aircraft. Here you can see sort of a concept drawing of what that would look like, basically putting material only where it's really needed to provide the stiffness and the strength that you need. All right, so typically what will happen is we'll have some initial design space. We'll start with that. We'll have some loadings, some fixturing on that design space. We'll create a finite element model within that space. We'll optimize it and get to an optimized topology, right? Then what we have to do is we have to take that topology and smooth it so we can print it better, and do a little bit of maybe shape optimization on it as well to see if we can improve it just a little bit after we've smoothed it, and then we eventually get the geometry that we can print. All right, so let's talk a little bit about how that process occurs, okay? And so one of the things I suggest that you do is that you pause this video for a minute at this point, and then go to the accompanying video where I'm demonstrating the use of some MATLAB software that will allow you to do topology optimization, right? And once you've seen a little bit of that demo, then come back to this video and I'll tell you a little bit about the rest of this video is going to tell you a little bit about the underpinnings behind that software, how it works, and how it adjusts the design, right? So first, we can think about a topology optimization problem. Okay. And the problem is that we're generally solving is to find the distribution of material in a prescribed area or volume, and that's known as the design domain. Okay, that minimizes the compliance, okay, which is a measure of the work done by external forces subject to an area or volume constraint, right? Which is also known as a volume fraction constraint. Okay, so mathematically, here's what that looks like. What we're going to try to do is find the values for some design variables. We'll call this X, okay? Okay, that minimize a measure of compliance. So this is C, and I'll tell you a little bit about what some of these other variables mean in a few minutes, okay? And that compliance is measured as the product, the tensor product of force, displacement, as a function of this vector of design variables with a little tilde over it, and I'll tell you a little bit in a second what that means, subject to a constraint on what we call volume fraction, okay? Okay. And in this case, these X's are all right, are elements of a domain where that domain is defined as values of X that are real, right? With X less than or equal to 1 and greater than or equal to 0, right? Those X's have real values, okay? Now let's do some definitions, right? So we're going to find the values of these X's, and there's an X associated with each finite element in our domain. So we're going to take our domain and break it up into finite elements, a lot like you saw in that video. And then what we're going to do is we're going to apply loads to that finite element. From the loads, we're going to be able to calculate displacements. And between the forces and the displacements, we'll be able to calculate the compliance, which is C. And then we're going to calculate what's called a volume fraction, which tells us how much material we have in the domain and make sure that it's less than some limit that we've set, which in this case will be VC, okay? All right, and so some of the definitions of our terms. All right, talk about that. So X here is a single valued variable. element density. X bar is a vector, right, of element densities. All right, XE in this case is defined as the density of element E. Okay, and that density is always between 1 and 0. Okay, X tilde E, all right, is going to be equal to a filtered, what's called a filtered density of element E. Okay. C as a function is going to be a function of these filtered densities. And that's defined as, these are all defined as the compliance of the domain, of the entire domain. Okay. F in this case is a vector of nodal forces. Right? So any forces that are applied to the domain. U, vector U, which is a function of the filtered densities, is defined as the vector of nodal displacements. Okay, we're going to have to solve a finite element analysis problem to be able to get that. And then V, right, as a function of these filtered densities is defined as the volume fraction constraint. Okay, where VE, right, is the volume of vector of element, of element E. Okay, and V bar is the vector of element volumes. Okay. VC in this case then is defined as a prescribed limit on volume fraction for the entire domain. All right, so if we think about these elements in 2 dimensions, right, so some topology optimization algorithms are defined in 2 dimensions. We take a 2-dimensional domain. This could be, say, a cantilever beam with a load maybe being applied over here on the side and fixed boundary conditions over here on the left. We would take that domain and we would divide it into finite elements, maybe a grid of finite elements. And you can see that grid taking shape here. And each one of these would be an element E, okay? And XE would be the density of that element E, okay? If we have a 3-dimensional volume instead, a 3-dimensional domain, right, like we do in the examples from MATLAB that I've shown you in the accompanying video, then what you're going to do is you're going to break it up into 3-dimensional finite elements, right? So those are going to be divided like so, divided like so, right? Divided like so. Okay. And then in this case, each one of these elements here, right, is going to be a 3D element E. Okay. And that element is also going to have its own density. Okay. All right. So again, if you haven't had a chance yet to go over to the other video and take a look at it, this would be a really good time because it'll motivate all the different things that we're talking about now in this lecture. So let's talk a little bit about density, right? What is it? This is a really good time to talk about it. So let's start talking a little bit about density. So what is XE, right? And then as a corollary to that, we also need to talk about filter. So what is XE with the tilde on top of it? We also need to know that. All right, so in this case, we've talked a little bit above about what XE is. And so if we then think about a grid like this, right, up above, we can have all sorts of elements and they each have their own index, right? And they'll go all the way down to element n down here, right? This is the nth element that we have. And so each one, each XE, right, it has a value of 1. So it's typically XE is less than or equal to 1, but greater than or equal to 0. And so if the value of XE is equal to 1, that means that that particular element is fully solid and is typically represented as black in the videos that we see and the topology optimization algorithms that we see. If it has a value of 0, then it's fully void. Okay, and then that will be represented as a white element, right? And these x's, all of these x's, x1, x2, x3, all the way through xn, are variables to be adjusted. Okay, that's how we adjust the material in each individual element. So the next thing we do is you'll see that in most of these equations previously, you'll see when we calculate compliance, which is the C, when we calculate volume fraction, which is the V, it's a function not of the original density, but of a filtered density. So let's talk a little bit real quick about what that is. So let's talk about filtered density. Okay, and that would be an x tilde, right? So x tilde here, let's call x tilde sub I, is equal to a weighted sum of the densities around a particular element. So let's see what that would look like. So sum, okay. Okay. So in this case, V sub j here is defined as the volume of element j, right? So how big is it? What's its of element xj? How big is it? Just in case some of the elements are different sizes. And so Ni here is defined as the neighborhood. The neighborhood of element xi. Okay. And so Ni here is defined as j, such that the distance between I and j, okay, is less than or equal to some r, all right? And r is the size of the neighborhood. Okay. All right, so I think in the software that you guys are looking at, right? That large R is represented as R min in the software, right, that you're using, okay? And in this case, Hij is defined as a weight factor. And so it's typically whatever that radius is minus the distance between the element I and the element j in question, such that j is in the neighborhood, okay? So this neighborhood Ni defines the distance around an element that will be used to capture other elements for this filter. And h is the weight, and the weight that's placed on other elements is based on how far away they are from this particular element. All right, and so if we go back up to this main equation here that we were looking at, and we think about, well, what is this weighted x? Well, on the top, it's the sum of a weight times how big that element is, times its value, its density, and it's divided by, it's normalized by the sum of the weights and the volumes of all of those elements. And in order to be counted here, the element J must be part of the neighborhood, right? And that neighborhood Ni is defined by a radius R, right? So if we go back and we look here at one of these elements, right? Let's say this is the element in question, right? And we define a particular radius R, right? Then every element that's within that radius can get counted, right, as a weighting function, a smoothing function. It counts as being part of that neighborhood, right? So typically that radius is just a little bit over 1 so that you can get, I didn't draw this very well, but if it's a little bit over 1, typically what you'll get is all the elements that are adjacent to it are counted as part of the neighborhood. Right? So what it does is it says, okay, whatever density you had for that element originally, replace it by a weighted sum of that element's density and all the other elements that are within its neighborhood, right? The farther away the element is, so the further the distance between the center of the element and the center of a neighboring element, the less weight it gets in this weighted sum. So why would you do something like this? Why would you do something like this? So sometimes in topology optimization, we can get something that's called a checkerboard pattern. So if we have a 2D design like this, right, and maybe these are elements, right, instead of making, and let's say, you know, we had a load across the top, but we could only afford to use so much material. One of the ways that topology optimization might decide to put material in there is in something that we call a checkerboard pattern, right, which doesn't really make much sense. We couldn't make this structure very well. The joints at which these checkerboard pieces come together would be incredibly weak, and the whole structure would be not very structurally sound. So instead, what this filter does is it tries to take each element and replace it by what's around it. So it would look at one of these solid elements and say, hey, you know, there's no material around it. So let's weaken the density of this one, maybe strengthen the density of another one. And what it eventually might do is it could, for example, in a case like this, let's say you've got, you know, a structure like this that's really checkerboarded. What it'll do then is it'll end up putting the material, instead of this checkerboard pattern, it'll put it all, say, in the center in a contiguous path because it gets better support from that, right? So the reason for a filter is to avoid what we call checkerboard results, okay? It avoids checkerboard results that alternate between solid and void. It smooths them out. Right? We don't want those types of results because we can't make them. They're not physically realizable. So it basically filters them out. All right, so the next question we want to ask, let's go to our next stage, is how does density affect material properties? Okay. Okay, so let's take a look at the most common density-based approach. Okay, and then we'll look at the approach that is implemented in this particular software, which is really very similar. So the standard approach, all right, or the original formulation, looked a little bit like this, where the modulus of elasticity in an element is equal to its density raised to a power times the modulus of the solid material. All right, so E naught here is the modulus of fully solid material. This is the modulus of element I. Xi is the density of element I, where xi is between some value 1 and some minimum value, right? And P here is what's called a penalization factor, or penalization power, where P is greater than 1, okay? All right, so if P equals 1, then we have pure interpolation. Right? So if xi equals 0.5, then that implies that EI is equal to 0.5 times E naught, or 50%, right, of E naught, right? All right, if that's the case, then what we would typically do, if we kept it at that value, we typically get a topology that was very grayscale. So a lot of intermediate density elements that aren't fully solid or fully void. And in this case, we really wanted to converge to topologies where we have a lot of solid and a lot of void and not a lot of material in between, because often that partially dense material is difficult to fabricate, right? You're going to make something in DMLS out of 316 stainless steel. What does it mean to be 50% dense stainless steel, right? It's really hard to realize something like that. So typically, a value of about 3, right? And why? Right? Again, that's to encourage convergence to solid and void, rather than intermediate densities. Okay. So for example, at P equals 3, right? If Xi equals 0.5, EI is going to equal to 0.5, right, raised to the third power times E naught. Right? And that's going to be 0.125 E naught. Whereas the volume fraction, right, at that value is actually going to be 0.5 times whatever volume that element occupies. So this element is not worth its weight. Okay. So you get a fairly large weight penalty. It weighs 50% of a fully solid element, but yet its stiffness is only 12.5%, right? Versus, right, if xi equals 1, right, then EI equals E naught, right, 100%, and VI is equal to V. So 100% of its weight, 100% of its stiffness. 50% of its weight, only 12.5% of its stiffness. And it's even worse if the density is lower, right? And so that's how we encourage it to converge to fully solid with a density of 1, fully void with a density of 0, right? And so then you might ask, why is X min greater than 0, right? And the answer is, where xi, remember, is always less than or equal to 1, but greater than or equal to this X min. And the answer is to avoid a singularity in our finite element matrix, which we'll talk about in a minute, right? So we don't want to have elements in there with 0 stiffness, because then when we try to solve this problem, F equals Kx, becomes very difficult to solve, because this stiffness K is going to be, it's going to have some 0 values in it. Okay, so we can't, the stiffness can't be 0 if we're trying to solve for displacement when we apply forces to it. Okay, so a quick update here in the MATLAB software uses a slightly updated approach And so the way it uses it is it does this. It says EI as a function of our density is equal to E min. Okay, so you specify some minimum value for the modulus that it can't go lower than, is equal to the density raised to the power P times E naught minus E min. Okay? And so here, xi can now be anything between 0 and 1, right? And so now this element density xi, it's still the element density just like before, enters into the equation here. And it basically helps us interpolate between some minimum value of our modulus and the value that it would take if it were completely solid, right? And so the only thing updated we have to do is we have to say that we're going to use our filtered density, right? Okay, with the filtered density somewhere between 0 and 1, right? And this is what's in the MATLAB software that I'm sharing with you, okay? So that's the modulus of elasticity for any element that's in our grid of elements, right? So if we go back here and we look, we say, okay, if this is, for example, our three-dimensional finite element analysis, right? Our finite element decomposition, our finite element mesh. This is our 3D mesh. Each one of these elements in here will have its own density, X. We'll use a filter with a particular radius to smooth out that density so we don't get checkerboard patterns. Then we'll take that density into this equation that we just derived to figure out what the modulus of elasticity will be for the material in that element, right? So if that element is fully solid, it's going to have the maximum modulus of elasticity E naught. If that element is fully void, has no material in it, then it's going to have the minimum modulus of elasticity E min. All right. Now, the last thing we need to think about is how are we going to analyze the properties of this structure. All right. So let's talk a little bit about the finite element analysis. Right? And how does this modulus of elasticity come into play here? All right, so let's do just a little bit of preliminaries. Right, we don't have time to derive the full finite element analysis, but in 3D, okay, typically in this MATLAB software and other software, if you have a grid, right, each of your finite elements, right, is going to be an 8-node hexahedron. Okay. Now, each node in this hexahedron, now, what does this represent? This is in a 3D finite element mesh for topology optimization, all right? So we've got an 8-node hexahedron, right? It's a cube. It has 8 nodes. Each one of these cubes represents one element in our 3-dimensional finite element mesh. So again, going up here to the right, one element in our 3-dimensional finite element mesh. Okay. All right. So we've got an 8-node hexahedron. Each one of these nodes has 3 degrees of freedom. Okay, so if you take a node, it's going to have a degree of freedom in the Z, a degree of freedom in the X, and a degree of freedom in the Y. Okay, so that implies that we have 24 degrees of freedom per element, right? Because we have 3 degrees of freedom per node, and we have 8 nodes, and 3 times 8 is 24. All right, so per element, what we have is a finite element equation that looks something like this. So the force that you apply is equal to the stiffness, all right, times the displacement. And I'm putting bars over here because these are either vectors in the case of F and U or a matrix in the case of K. So then this would be a 24/1 vector. This would also be a 24/1 vector. And this would be a 24 by 24 matrix. Now, this is per element, and then per object, in this case, that's an assembly of elements. So we've got lots and lots of elements in our domain. Then we assemble these and we have F equals K U, right? And so this is the vector of all applied loads. Right? This is the vector of nodal displacements. Some of which can be fixed, as we do in our MATLAB code. And this K is the assembly, basically an addition or aggregation of all of the element level AEs. Okay. All right, now we still haven't tied this back yet to our density, right? So in 3D topology optimization, right? We then have force, right, is equal to our stiffness matrix, which is a function of our filtered densities, times our displacement, which is also going to be a function of our filtered densities. All right. Now, the material properties come in to the stiffness matrix. So if we look at how we formulate that stiffness matrix, it looks a lot like this, right? So it's a sum from I equal 1 to n, right? Where n is the number of finite elements of E min, remember that formula for calculating our modulus? Okay. All right. So Ki naught here is a constant matrix, right? For each element. It's just a matrix of constants. And then E min is our minimum modulus of elasticity as we defined before. E naught is the modulus of a fully solid material. P is the penalty factor, and Xi is the element density, right? And so this is where our element densities come in. This is where our penalty factor comes in. And then this is also where that radius, that R min, comes in. This is our penalty, right? All those factors come in to determining the stiffness matrix. And then we solve that. We solve that to determine the displacement, right? And then we use that displacement to calculate compliance, right? So let's go back to our original formulation, our original problem formulation, and look at that one more time, right? All the way up at the beginning, our original compliance, our original problem formulation was to find the values of these x's. So these are the densities of each of the individual elements. Those densities then help determine the displacement that goes into this compliance equation, right? Right? These are the element densities. Find the values of the densities of each element that minimize compliance, which is the forces, the applied nodal forces times the displacements. And the displacements depend on the densities, right? Because F equal Ku, and the K stiffness is a function of these densities, as well as the penalty factor and our smoothing function as well. And then it's subject to this volume fraction constraint here. So we can't just, if we really wanted to minimize compliance, we really wanted to minimize displacement, we'd just fill the whole envelope full of material, right? Max it out. Why not? But then that wouldn't be a very interesting problem because that's really what we started with, which was a full domain full of material. So we've got a volume fraction constraint here that's going to constrain it and say, oh, you can only fill the material domain with, say, 30% volume fraction, right? So that's going to constrain what we can do with it. And so then finally, the other thing that's operating in the background, right? I'll do this. So iteration is solved by optimization algorithm. Okay, and so what it does is, what does it do? It adjusts the vector of x's, right, to minimize compliance and satisfy our volume fraction constraint. Okay. In this case, what we've got, the algorithm here is an MMA algorithm. The MATLAB code that I'm showing to you, an MMA here stands for method of moving asymptotes. All right. So I would recommend now, I know I asked you earlier to go look at the accompanying video where I was demonstrating some of the MATLAB code, the three-dimensional topology optimization in MATLAB that I've made available to you. Now I'd recommend that you go back and look at it a little bit more. So let me translate a few things for you. So here we call it R is our radius. In MATLAB, that's R min. So you'll see it listed as R min. And that's a density filter. So typically values might be somewhere around R equal 1.2 to 1.5, right? P is the penalty factor. And so typically those values of P equal 3 is about right. And then we've also got a volume fraction limit. Right. So we've also got a volume fraction limit, right? So we talked about that up in our original problem formulation. I'm going to scroll up here. We had it listed as VC, right? So we had it listed as VC. That's our volume fraction limit. And in the software, it's just called volume. Okay, and so a typical value there would mean somewhere around 0.3, right? And so you could just change it. So, typical values are somewhere less than 50%, but greater than, say, 10%, something like that. So that's called volume, okay? And in the software that we have, this is called penalization. So I think you'll recognize it when you see it, okay? All right, so I'm gonna close here and ask you to go ahead and go back and review that video that I took of the topology optimization examples. And then I've also given you the MATLAB code yourself to play around with. So I suggest loading it and taking a look, and you can play around and try some different problem formulations yourself.